Hey, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
We don't have a problem. Today I want to talk just about some more about current electricity. About currents, we're talking about a flow. Now, if you think about a water flow, so let's say I've got a pipe, and then water is flowing through the pipe at a particular speed. You could measure, for example, the number of gallons per minute, right? And in many ways, when we talk about electricity, it's really the same thing, is that there's a flow through a wire of a current, and we are not measuring like gallons per minute. We're measuring something else, but it is per second. We're measuring coulombs per second. Because if you think about a coulomb is a measure of an electron. So if you like to think of it in terms of current here, I can have a drop of water. So you might say, how many drops of water per second are flowing through a pipe? And I say a drop because it's a small thing. Because when we talk about a coulomb, we're measuring electrons, and electrons are very, 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 very small. So these electrons are moving through the pipe, if you will, and the pipe is made of some conductor. That means typically a metal, and the most common metal is copper. So when we talk about current electricity, the focus we want to talk about is, if you will, the math part of it, right? So if I'm doing the math part of current electricity, we use this symbol for current as an I. The I actually stands for intensity, and intensity is coulombs per second. The units are coulombs per second, so that would be charge per unit time. Now, it turns out there are other equations that you're going to need to use when you're doing some problems, et cetera, et cetera. And you've got an equation sheet, but a couple of key equations that play a role in here is that if we remember back to previous videos, we can find the potential energy of an equation in electricity, the U stands for potential energy, and that's equal to the Q times a voltage. And if you remember that a volt is a joule per coulomb, all right, watch what happens here if I take V times I. I just can do it dimensionally. If I take V times I, V is a joule per coulomb, and I times it by a coulomb per second. The coulombs cancel, and you get a joule per second. And if you remember what that is, a joule per second is power. So P equals V times I. And P, if you recall from previous classes, is measured in a watt. So you can find the power of a system by taking the voltage and multiply it down the amperage, or the I, because that's what they basically cancel out. And to take it one step further, if power is energy over time, which also equals VI, if I multiply both sides by time, the time cancels on this side, we can say E, now we probably should say U, the potential energy, is equal to VIT. So here are the key equations we've got, is that amps, which measures this, the rate of electron flow, of charge flow is really the better way to say this. So the equation is this. And if I want to find just the potential energy of a system, if I know the charge and the voltage, I can use that equation. I have another equation with power. Power equals VI. And then we also have power can also be equal to, if I want to find energy, energy is VIT. So these are the three new equations that you're going to use in this upcoming exercise. And I'm going to finish off with a thing that we want to focus in on, something called Kirchhoff's rule. It's about current, and just something that actually totally makes sense. So if I have, here's Kirchhoff's junction law says that the current entering a joint in a circuit must be equal to the current leaving a joint. So, a joint, that sounds weird. So let's say that this is coming in at 6 amps. What must come here is this could be 2 amps, and that makes this has to be 4 amps. Or whatever, right? Or if this is 3 amps and this is 1 amp, then this is going to be 4 amps. So the current in has to be equal to the current out. And again, that makes like 1,000% sense. If I've got water flowing through a system, and then it branches off. Let's say I branch off into a fat pipe and a skinny pipe, and I've got, 1,000 gallons per minute. So it's a big pipe like per minute. Then if this is coming in at, this is 100 gallons per minute, then this, of course, would have to be 900 gallons per minute, because all the water has to go through the pipes. And this is what's happening in wires. The current between the two has to always add up. It's called Kirchhoff's junction law. Hey, Houston, we don't have a problem. We'll see you in class.